Hi everyone, welcome to Basic Oilfield Hydraulics. My name is Toyosi Bamidele and I'll be taking you through this course. The topics we'll discuss will be pressure, force, buoyancy, material strengths. There'll be some additional information throughout the video, and there'll be some unit symbols and conversions throughout the video. So under pressure, we'll discuss hydrostatic pressure, bottom hole pressure, applied pressure, differential pressure, forces produced by pressure. So let's get into hydrostatic pressure. Pressure is the force per unit area. It's identified as force in pounds over area in square inches, which is your pounds per square inch, normally set as psi. Hydrostatic pressure is the pressure created by the weight of a column of fluid acting on a defined area. There are two factors to consider with hydrostatic pressure: your vertical height and the density of your fluid in pounds per gallon or pounds per cubic feet. It could be expressed in different ways. The following containers shown have the same hydrostatic pressure, but understand that hydrostatic pressure is not affected by the shape of the container. It's only affected by the height and the density, as said before. Therefore, the hydrostatic pressure in each of these fluid-filled containers is the same, as they have the same height, assuming the same density of fluid is in them. So let's get into this little depiction. Here, considering the pressure gradient of water, 0.433. Assuming this is 1 foot, this is 2 feet, and this is 3 feet. If I get my 0.433 psi per foot, and I multiply by 1 foot, I should obtain this. If I multiply by 2 foot, I should obtain this. And if I multiply by 3 feet, I should obtain this. And this is just saying the same point again. Shape and volume is not a function of hydrostatic pressure. Due to the difference in height of each of this container, the hydrostatic pressure at the bottom of each container will be different. So the next slide, we'll get into more of the equations that help us solve with hydrostatic pressure. So there are three methods, or two main methods, for calculating hydrostatic pressure. The constant factor method, this is very popular. It's a very popular equation using your 0.052 gallons or 0.05195 gallons per feet times square inch. So this is another way. Other than multiplying it by this factor, you can also get your 19.25 and divide it by your fluid weight, or if you want to deal in cubic feet, you can multiply by 0.07 cubic feet per feet square inch. The other method is the fluid gradient method, where you can obtain the fluid gradient method from your field data books. If you have any field data book handy, you can get your fluid gradient, and also you know your height. So by multiplying that, you can get your psi and get your hydrostatic pressure. Also, your API gravity method, when the API gravity of the oil is given. So you can get that by simply doing 61.25 divided by 131.5 plus my API, and I multiply by my true vertical depth. So in respect to height, there are two important measurements. It's very important to have a clear understanding of what the height you need for hydrostatic pressure. So the true vertical depth, this is the depth measured from the bottom of the hole straight up to the surface. A straight measurement from the bottom of the hole straight up to the surface. This is what we'll use for our hydrostatic pressure calculation. It represents the height of the fluid column, while the measured depth, which is mostly used in our volume problems, is the entire length of tubing required to reach our the bottom of our well bore. So this is your measured depth, right? This entire length, and this entire length is my true vertical depth. Let's get into some problems. So, given a non-deviated well, completely full of fluid, of 7,000 feet deep with a fluid gradient of 9.6 pounds per gallon, what is my hydrostatic pressure? So I know my fluid weight, I know the height of my fluid column, and this is a straight example. Bottom of my wellbore to the surface is 7,000. So I plug in my number, plug in my fluid weight, I multiply by 0.052. I get my answer in pounds per square inch, 3,494.4 psi. Next problem. Given a non-deviated well of 10,000 feet, the fluid in an annulus is at 3,000 feet. What is the hydrostatic pressure on the packer if the fluid weighs 11.8 pounds per gallon? So I'm giving that my entire fluid column is 10,000, and I'm saying that my fluid rests, the very top of my fluid rests at 3,000 feet. So I get my values. Understand that this will be 10,000 minus 3,000, giving me 7,000. I multiply by my fluid weight, multiply by 0.052. I get my answer in pounds per square inch. That is my hydrostatic pressure for my hydrostatic pressure on the packer due to the fluid in the annulus. Let's move on. Another problem. What is the hydrostatic pressure at the bottom of a deviated well filled with 92 pounds per cubic feet fluid, given a measured depth of 9,500 and a true vertical depth, your total vertical depth at 7,000 feet? So always remember, with hydrostatic pressure, we want to deal with the true vertical depth. So this is the equation that deals with cubic feet. So I plug in my true vertical depth, I multiply by my fluid weight in pound per cubic feet, multiplied by my factor. I end up with 4,508 psi. Easy peasy. Next, what is the hydrostatic pressure at the bottom of a 5,000 feet well if the fluid level is at 1,250 feet and the well fluid is 20 API oil? So I've given my API oil. Naturally, this should come into me. I know my API oil, so I can take my API gravity method formula. I know that 661.25 divided by 131.5 plus 20 multiplied by my true vertical depth. I also know that in order to get the height of my fluid, I have to subtract. So I go on and I do 5,000 minus 1,250. I get my height. I multiply by the pressure gradient or the fluid gradient. Then my answer comes down to 1516.125 psi. Let's move on. The last example for hydrostatic pressure. Given the following well conditions, what is the total hydrostatic pressure? I have fluid 1 of 15 pounds per gallon slurry, cement slurry, and fluid 2 of 5,200 feet of 9 pounds per gallon of water. So I have my water, this is the yellow color for water, and I have my cement slurry, which is my 15 pound per gallon cement slurry. So my question is, what is my total hydrostatic pressure? So I have the total depth of my well, I have everything. So first I want to calculate the individual hydrostatic pressures of both fluids according to their heights and add them up. So I plug in my 700, my TVD, the height of my, this should be for this blue fluid. So that should be the height of my cement, 15 heavier cement. So that means the height actually starts from here, not from here. And I multiply that by 0.052. That gives me an answer of 546 psi. So the height of my cement is from here to here 700. Then the hydrostatic pressure due to water, which is my height from surface to 5200. So I do 5200 times 9 pounds per gallon times 0.052 using the constant factor method. I add them together and I come down to 2,979 psi. Let's move on to the next example. What is the pressure in a 2,000 feet well filled with 9.2 gallon water or fluid to which 3 pounds of sand per gallon is added? So in order to get my solution, I have to use the weight of slurry. I have to find my weight of my slurry first. And the weight of my slurry can be obtained using this simple equation. Weight of fluid plus pounds of sand per gallon over 1 plus 0.0456 gallon per pound times the pounds of sand per gallon. So I know the weight of my fluid is 9.2. I add that to my 3 pounds per gallon of sand. I divide that by 1.0456 gallon per pound times 3 pounds per gallon. I end up with a fluid weight of 10.732 pounds per gallon. I go back to my constant factor method, hydrostatic pressure due to water. I take my height, my TVD, 2000 times 10.732 pounds per gallon times 0.052. I end up with 116.128 psi. So that's the end of hydrostatic pressure. I hope you've gained something. If you have any questions, put that in the comment section below or put them in the comment section on my blog, petrobasics.com. The next video will talk about bottom hole pressure, bottom hole temperature, and applied pressure, differential pressure, and so on. So this is part one. This is part one of oilfield hydraulics. Next will be part two. It was great teaching this today or discussing this today. I'll talk to you later. Have a good day.